I'm going to start my today's session, and my today's session will be based upon the discussion on continuous random variable. So far, we have discussed on discrete random cases. Continuous random variable is another type of random variable whose domain contains infinitely many values. We know that if a domain of the random variable contains finite values or countably infinite values, then the random variable is discrete. But if the domain of the random variable is infinitely many, then the random variable is said to be continuous. So in brief, if domain of the domain of the variable is infinitely many, then the variable is actually called continuous. Variable is continuous. Now, to understand the continuity, I can consider a very beautiful example, and you will, by that example, you will get to see that what is the basic difference between the continuous random case and the discrete random case. Also, in continuity, some bizarre thing happens that you will be able to understand by citing this particular example. So example goes like this. Also, in the beginning of our classes, not today's class I'm talking about, in the very beginning I talked about something of this kind, that I talked about that for any impossible event phi, the probability is always equal to 0. But I told you that the reverse of the case is actually not true. So by this example that I'm going to cite right now, by this you are going to understand what is the difference between continuous case and discrete case, and also you are going to understand about some features of this particular result. So this example goes like this. It is a very simple example. Suppose we have a stretch of road like this. Okay, this is the stretch of road. This is the starting point capital A, and this is the starting point. This is the end point capital B. And suppose this stretch of road has a distance of 200 kilometers. Okay, so this is the example I'm considering. And also, we consider that in this particular stretch of road, there is a section, say this section, that which has a distance of say 100 kilometer, okay, or say 50 kilometer, which I'm marking as CD, which this particular substretch has starting point C and the end point D. And this particular stretch CD, which is the sub-interval of the interval AB, suppose this stretch of road is actually accident prone. It's the accident prone zone. Okay. Now, any car moving towards B from the point A has some sort of probability of meeting with an accident in this particular accident prone zone. Okay. Now, if I ask you a question, what is the probability that the car traveling from A to B will meet with an accident, then what you can do with the given knowledge, you can say that, okay, if CD is the accident prone zone, you have this information with you from your past experience. So if CD is the accident prone zone, and if the stretch of the length is 50 kilometer, so the probability of this particular event will be given by probability of the event capital A that the car will meet with I'm not considering it to be A because A is the starting point. Probability of the event X that the car will meet with an accident when it runs from A to B will be given by the length of the interval CD, which is the favorable case, divided by the length of the interval AB, which is the total case. And remember, here we shall consider length to be our favorable number of events because it is this is the continuous stretch of the road and there is no breaking point. And always remember that probability is a measured theory, so we can measure the number of events by any means. So in a very easiest way, we can say that this probability is given by as length of CD is 50 kilometer and the length of AB is 200 kilometer. So the probability of such event occurring is 1/4. So we got that we can easily find out the probability of a car meeting with an accident in this particular accident prone zone, provided we have the information of this accident prone zone. Okay, otherwise not. If the information is missing, we'll not be able to find the probability at all. Now, for example, suppose in the same case, if I modify this particular system a little bit in the following manner, suppose, for instance, it is a theoretical argument that I'm placing over here right now. Suppose the same stretch of road is considered, and now suppose this is the accident prone zone whose length is a mere 10 kilometers. So obviously the probability is going to change somehow. Okay, the probability will be then in that case, the probability of X will be 10 kilometer by 200 kilometer, that is 1/20. So probability is actually decreasing. And suppose the probability in this case, now I'm considering the stretch of the road AB once again, and suppose the probability is being considered, the accident prone zone is being considered over here as this. Suppose this is the accident prone zone. There is a kind of quick turn which has a kind of a length 5.5 kilometer or some sort of bumper is there. So whatever it is, so some sort of thing is there for whose length is 0.5 kilometers. So in this particular case, the probability of the event will be 0.5 by 200 kilometers, which is pretty small, very small. Now, in a similar manner, by placing the theoretical argument in the following way, if I consider the same stretch of road capital B, whose length is 200 kilometers, and suppose I am infinitely decreasing the length of the accident prone zone. Theoretically, I am decreasing the length of the accident prone zone in such a manner, in such a way that it tends to a point, single point. It tends to a point. Okay, so theoretically, suppose this is the point at which the accident takes place, whose length is tending towards 0, because a point doesn't have any length. Okay, breadth, we know this very well. So this is infinitely small point, and this length is pretty small, which is negligible. So obviously, if this is the case, if we do such a kind of thing theoretically, because it is practically not possible, then in this case, the probability of the event capital X will be tending towards 0. That probability will tend towards 0. And we know that a particular line, here the line that I'm considering is AB. This line is actually consists of infinitely many points on it. If I join these infinitely many points, we actually get the line. And somewhere in this particular collection of points, some points are accident prone according to my theoretical argument, whose probability is actually 0. So what we can say that for each and every discrete point, considered over here in this theoretical, in this particular thought experiment, the probability of the accident, for the accident to probability that the car will meet with an accident will become a 0, will become negligibly small, and therefore it will tend to 0. But this is not the case. If there is an accident prone zone, then suppose this is the accident prone zone. In this particular stretch, if I consider infinitely many points, infinitely many discrete points, at each of these discrete points, the probability that the car will meet with an accident is 0. Suppose this is my favorable stretch of road where the car actually meets with an accident. Now this favorable stretch is actually the part of the straight line, and that can also be treated as the collection of infinitely many points. By the theoretical thought experiment, at each of these infinitely many discrete points, the probability that the car meets with an accident is 0, but the car can meet with an accident, and therefore, although at these discrete points the probability is 0, for this continuous stretch the probability is definitely not 0. Okay, so therefore so what we can consider for the case of discrete case, the similar situation cannot be considered for the continuous case. For continuous case, the situation actually changes. And also we can say that we know if phi is an impossible event, this implies that probability of phi is equal to 0. But if there is an event capital A for which probability is 0, that doesn't always imply that A is impossible. The converse of the theorem is actually not true. Why is it so? Because although at each of these points the probability is 0, but the accident will happen. We cannot say that the accident will happen, this particular event is impossible. It cannot be. It is always a possible event, a possible consideration. So therefore, in discrete case and in continuous case, the situation actually becomes different, and in continuous case, however, we say that the situation becomes a little bit of bizarre than the discrete case. Therefore, I actually use the word bizarre. Okay, so this is the thing that I wanted to tell you. This is the example that I wanted to cite to make you understand the difference between these two. Now there comes the probability distribution for continuous random variable. The probability distribution for the continuous random variable will be a kind of chart where the random variable x will take some values in a certain range. So it will take, the x will take some values within a range. The domain, basically the domain of x will be a range. Will be a continuous range of values. And we will be having some sort of probability function which we define by fx now for x lying between some sort of interval a b. Okay, so this sort of probability function will be given in case of continuous case, and there may be different forms for expressing this probability function. So here probability will become a kind of function. Previously it was also a kind of function, but having some sort of discrete values. Now it will be having some sort of functional form, like I can consider not only a functional form, but it should be a valid functional form. So in this manner, if we can get a kind of chart, then we'll say that this is a kind of continuous probability distribution. And just like the discrete case, we can also consider some properties of this continuous probability distributions. Rather, as you know that in case of discrete case, in case of discrete random variable, The probabilities associated were known as probabilities associated were known as probability mass function. Probability mass function. In here, in continuous case, the probabilities associated will be known as probability density function. Probability density function, or PDF. Now, this probability mass function and probability density function, basically they are same things. They are actually probabilities, but we give them two different names just to distinguish the two probabilities from one another. Just like we give the two twins the name like Ram and Sham, just to understand that they are twins and this is Ram and that is Sham. They have they have some sort of difference between them. Maybe that is only known to the parents, not to any other people. Similar situation, the two probabilities have been named as probability mass function and probability density function. Just to remind us that if I talk about probability mass function, that means I'm talking about the discrete case. And when I'm talking about the probability density function, I'm talking about the continuous case. And just like the probability mass function have two properties, as you can recall, the properties where probability of x equal to small x is greater than or equal to 0. This was the first property. In probability density function case, we have a similar sort of property, which is fx greater than or equal to 0 for all x in the domain. So this same property are actually holding over here. Second property that we considered in case of probability mass function was as follows. We said that if I consider all possible values of x for which the probabilities are considered, then this total probability is equal to 1. In case of probability density function, we consider all possible values of x from the domain and we integrate. Here in continuous case, integration is this actually considered to be the summation. If we integrate with respect to x, then that probability, the total integration will be equal to 1. So this is the total probability of the continuous case. This is the total probability of the discrete case. Also in discrete case, we found the average of the random variable. If capital X is the random variable where x is discrete, the formula was given by summation over x into probability of x equal to small x. In continuous case, what we do is that we calculate the expectation where x is continuous, but what we do, we consider each value and their corresponding probability fx. We consider this, we take the probability function, we multiply with this by the value x, and we integrate over x dx. That is the form of the expectation in case of continuous random variable. Similarly, we can calculate the expectation of x square. Expectation of x square in case of discrete case was the following. It is summation over x square into probability of x equal to small x. In case of continuous case, we calculate this expectation of x square as we multiply the function by x square and we integrate over all x. And once we calculate this expectation of x square, lastly, by the same old formula for Vx, we can calculate the variance of the random variable. The formula of Vx is actually not changing. It is the difference of expectation of x whole square and expectation of x square. So this formula will be considered to calculate the variance of the random variable capital X. So this is the way by which we actually deal with the continuous random variable. The situation actually doesn't change. What changes is the form and the way by which it is calculated. Only thing you have to remember is that in place of summation, we have to treat the thing, problems with respect to integration, because integration is the process by which we calculate the probabilities uh, in case of continuous random variable. And also this particular result is actually very important, that if the impossible event is any impossible event is there, its probability is 0. But the converse of the theorem is not true, that if an event is 0, its probability is not, its probability is 0, then it doesn't imply that the event is always impossible. And for which we consider the accident example, where probability for each of the discrete points was 0, but the event accident was actually not an impossible event. Okay, so this is the first important thing that I wanted to talk about. The second important thing, the important point that I want to say to you is the following. You can recall that when we, in case of discrete random variable, suppose x is discrete, and whenever we wanted to calculate probability of a less than or equal to x less than or equal to b, what we actually did, we considered the value probability that the x takes the value a. Then we considered any other value that x is taking inside this range, and then we added probability of x, probability that x takes the value b. That was the way by which we calculated probability in case of discrete random variable. But if the situation was like this, the probability of a is less than x less than b, where equality sign is not there, what we actually do, we calculate the probability in the following manner. We consider the in between points only, where a1, b1, they are actually lying between a and b. a1 and b1, these points are not a and b. These 2 points are excluded from the picture. Okay, so we will not consider these 2 points over here. Similarly, if we consider probability of a less than or equal to x less than b, so here we consider probability of x equal to a, and we go on, we move on, but ultimately we stop at x equal to b1, but we do not consider the point b because the equality sign is not there. And similarly, if we consider probability of x equal to probability of a less than x less than or equal to b, we start from the point, discrete point, say x equal to a1, and we go up to probability of x equal to b, but we do not consider this point. So this happens, all of these things happen if the case is discrete. But amazingly, in continuous case, if x is continuous, what we do is that, what we see is that probability that x is taking values between a and b, where a and b are inclusive, is equal to probability that x is taking value between a and b, where a and b are exclusive, is same as probability that a less than or equal to x less than b is same as probability of a less than x less than or equal to b. So it is also a very important fact that in case of continuity, whether you are including any point or excluding any point doesn't matter, doesn't change the probability at all. So probability of calculating that x greater than 0 for some probability function will be same as probability of that x greater than or equal to 0. Remember, so the probability actually doesn't change because it is a continuous case. But if it is discrete case, then we have to take into consideration of the points, of the individual points that the function is considering at different points of time. So this is a very important point that you have to keep in mind. Now, a quick example that I'm going to show you. You are going to rather do the calculation by yourself. Okay, so the problem goes like this. Let capital X be a continuous random variable, with probability density function with probability density function given as follows. Suppose fx is given as a into x when x is lying between 0 and 1. Fx is a when x is lying between 1 and 2. Fx is minus ax plus 3a when x is lying between 2 and 3 and 0 elsewhere. You can do one thing. Here the equality sign I'm not considering. Here I'm writing only less than symbol, and this equality that x is taking value 2 is being written over here. From here I'm considering the equality symbol. I'm not considering the equality symbol. The equality symbol is being considered in this particular case. X is greater than or equal to 3. This means x is greater than or equal to 3. Okay, so this is how the function is defined. Now your job is to determine, question is determine the constant a, and number 2, compute that probability x, compute the probability that x takes values less than 1.5. This is the problem that we are going to consider over here. A very simple problem. So first of all, what we are going to do is that we are going to find the value of this constant a. Now we know from the property that we have already discussed that if we consider all possible values of x, and if I multiply the function with the not function, if we consider all possible values of x and we actually integrate the probability function fx with respect to x, then the total probability is actually equal to 1, which implies that, and since these values, this x is actually the real number, and we know that the real number set is actually denoted by this interval minus infinity to plus infinity. This is the real number set. Okay, and since each of the random variables are actually each of the values are real numbers, so we can write this particular expression in the following manner. It implies that we are integrating from minus infinity to plus infinity of the function fx with respect to x, so that the total probability is equal to 1. But the function is defined in this particular ranges. The range is very important over here. Just look at it. So what we are going to do, we are going to break the integration into several parts. First of all, we are going to write it in the following manner. We are going to break it into 5 parts. Minus infinity to 0 fx dx. This is the first part that I'm going to write. Then we are going to write it as 0 to 1 integration fx dx. Then we are going to write it as integration 1 to 2 fx dx by the property of the definite integral. I'm writing it. Then we are going to write it as integration 2 to 3 fx dx, and then 3 to infinity fx dx. So in these 5 parts, we are going to divide the entire integration range from minus infinity to plus infinity. Now you see, when we talk about elsewhere, we simply do not mean x greater than or equal to 3. We also mean this one another thing. Here we have, although I have written x greater than or equal to 3, we had to consider another possibility, that is x when x is less than 0. So when the real number is negative, is less than 0, then also the probability is 0. That is what we mean by elsewhere. Okay. So with this definition, in this particular range, that from minus infinity to 0, the probability will definitely be 0 by this particular value. And for the last one, that is when the x is taking value greater than 3, the probability will be 0 again from this particular part. And what we find, that from 0 to 1, the function value is equal to ax dx. From 1 to 2, the function value is a dx. Function value is a, which is a dx. And for 2 to 3, the function value is minus ax plus 3a from 2 to 3 dx. So our next job is to integrate this function. We integrate this function, which is very simple integration, and we can find out the value of a from here. So just I'm asking, we have time, we have 8 minutes. Just do this quick integration and tell me what value is coming. I have the value with me. So if you give me the right answer, I can verify now. So please tell me what is the, if I integrate this quantity, what is the value of a? What value you are getting? So I'm waiting for your reply. Just make it fast because this is the only session that we are doing right now. After this session ends, that you are not going to join once again today because you have another session from 4 p.m. So just quickly tell me what is the value of a. These two portions I have written because in these regions, the probability, the functional value is, the probability is actually 0, which is being written from this particular part, last part. That is when x is less than 0, the probability is 0. When x is greater than or equal to 3, then also probability is 0. Remaining portions have been written from the other 3 parts. That is from 0 to 1, the probability is taking this type of form, ax. From 1 to 2, the probability is taking the form a. And from 2 to 3, the value is taking the form minus ax plus 3. So we are actually putting the probabilities of this form inside as integrand in these 3 possible cases. And then your job is to integrate and put the limits to find out and equate it to 1, because the total probability is 1, to find the value of a. So what value you are getting? And remember, this value has to be a positive value, because if a is not positive, negative, then the function will not be valid function. According to the book that from which I have selected the problem, answer section, it is given a different value, not 2 by 3. So just recheck the calculation and tell me 2 by 3 is not the value. Yes, half. So the value that is coming, the probability that the value of a that is coming is half. So a is the constant, a is half. It is matching now. So the first part is done. Now quickly I am going to talk about the second part. In second part, you are going to find the probability that random variable x takes value less than 1.5. So how can we calculate this? So probability that x takes value less than or equal to 1.5. This actually means, in case of continuity, that x, the random variable x, is lying between minus infinity to 1.5. This is the meaning of this. So now if I want to write it in terms of the integration, we can put it in the following manner. So integration minus infinity to 1.5 fx dx. Now just look at the function. Look at the function. Function is defined from 0 to 1 and then from 1 to 2. Just look at these 2 sections. Okay, now I'm going to do something over here. I'm going to break the integration into 3 parts. First of all, I'm going to write it as minus infinity to 0 fx dx. And then I'm going to write it as 0 to 1 fx dx. And then I'm going to write it as 1 to 1.5 fx dx. But we know as before that in this particular section, the probability value is 0. So this entire integration will be 0. When x is taking value 0 to 1, the integrand will be ax. So this will be ax dx. And in the last case, that is from 1 to 1.5, 1 and 1.5, this interval is actually the sub interval of 1 to 2. And therefore, if in the interval 1 to 2, the probability is A, so in the sub interval also the probability will be A. So here in this particular case, it will be 1 to 1.5 A dx. Now you are going to integrate it. It will be A into x square by 2, 0 to 1, plus ax 1 to 1.5. And then you are going to put the integration, the limit, which will be 1 square by 2, that is half, minus 0 square by 2, and that will be 1.5 minus 1. So this will be a by 2 plus a into 0.5, that is 2. So that is equal to a by 2 plus a by 2, that is a, and your a is actually half. So this probability that x takes value less than or equal to 1.5, that is also equal to half. So this gives you the answer of the problem, of the thing that the random variable x takes value less than 1.5. So this is how we actually calculate the probabilities here in this particular case. Two more questions that I can add over here, that you can try it at home in your leisure time. Here in this particular problem, you can try to calculate ex square and vx. Try to do this particular calculation and try to see how what sort of value comes out of it. So this type of problems that you may encounter in this particular chapter in the examination. Okay. Tomorrow we are going to discuss about some special case of continuous probability distribution. And since now the time is running out, I'm going to end my today's session. Tomorrow we are going to meet once again in my scheduled timing, that is at 1:40. Till then, bye. Okay. Thank you so much for joining.